Hello. It is wonderful to see all of you here this evening at the Royal Institution. I am Professor Ricketts, and it is our intent this evening, in return for the honor that you do by coming here to see what are our proceedings, to bring before you in the course of this lecture the chemical history of the candle. Now, Professor Faraday has taken this subject on many a former occasion, and were it left to his will, so he says, he should repeat it almost every year. For there is not a law under which any part of this universe is governed which does not come into play or is touched upon by these phenomena. There is no better, no more open door through which to enter into the study of natural philosophy than by considering the physical phenomena of the candle. I trust, therefore, we shall not disappoint you this evening in discussing this topic, rather than some newer topic, which could not be better, were it even so good. And before proceeding, I would like to say that although our topic is great, and our intent is to treat it honestly, seriously, and philosophically, yet, to pass away from all those seniors amongst us, and as Professor Faraday has in the past, I claim the privilege of speaking to the children here as a child myself, at least at heart. So I hope you will allow me into speaking in a familiar way to those whom I esteemed nearest to me on this occasion, the young philosophers tonight. Thank you for coming. Now, unfortunately, Professor Faraday is not able to join us. For obvious reasons, he's popped his clogs. But he has given me his notebook from his last lecture on the 8th of January, 1861. And this notebook contains a plethora of insights into the physical phenomena of the candle and of the world. And he's marked a page here for me, and he's underlined something. Let me just get in the light here. David, please make sure to take care of my notebook, and please make sure not to burn it in the lecture. For those who are wondering, no, this is just a copy. Faraday's real notebook is right here. Charlotte, can you open it to the page, or may I?
Yes.
So I did not burn Faraday's notebook. Where is it?
It is in there.
Oh, I should have marked the page with flash paper.
We will find it.
Did you pull it out, the page he burned? All right, we'll just leave it there. You can see almost on every page, he somehow managed to burn a page in his... there we go. Thank you very much. He burned his own notebook, so I feel at home in burning my copy. Thank you very much, Charlotte. So we come here as philosophers to understand both the beauty and the function of the candle. And as philosophers, we need to make sure that we are objective in our view so that we can understand the scientific principles. Now, you, like I, may be thinking, what is so special about a candle? Well, I can tell you that there's much about a candle to teach us about both our physical world and also about ourselves. So I'd like to begin with thinking about a candle. I'm sure all of you at one point or another have held a candle or seen a candle. What might be some of the first observations you have? Well, I think first, it's warm. But a fire's warm, so it's not very surprising that a candle would be warm. The candle gives off light, So does a fire. But does burning always have to give off light? Let us start our journey together with finding the answer to this question. Judith and Tom, would you please come and join us?
Thank you. Hello, everyone.
Hello. Professor Ricketts just invited you to think about your expectations of fire. What will you see? Here we have two fuels. We're going to light them and see if your observations will match your expectations. So if I light my first one here. Oh, we got a nice, obviously it was nice, it's bright. I don't know if you can feel it from here, but here it's quite warm.
Let's see what happens if we light the second one just here. So there is a flame, but it's really, really hard to see it. So just to prove to you that it's actually burning, I've got some cotton, and it's definitely burning quite rapidly. I think so that people can see it a bit better, Tom, why don't you turn yours off? And Josh, can we bring down the lights a little bit? So there we go. That is the flame. This demo proves that for things to burn, they don't actually need to shed a very strong or bright light. Things can burn without it. And the candles are really, really special because they burn with a bright light. And to tell us a little bit more about that, Professor Ricketts is going to come back.
So I hope from that you may start to think that maybe the candle isn't so ordinary. There's questions I hope tonight that you will have answered for you, and hopefully ones that you'll answer for yourself. So I'd like to begin investigating the candle to ask, what is burning? So I take this splint and I take it next to the candle. I'll do both sides. But you'll notice the solid wax does not burn. Maybe difficult to see, but over here there's a candle filled with melted wax. If I stick my taper in, the melted wax does not burn. So the question is, what is burning in the candle? So I have a tube here. It is a glass tube. For reasons of many, many practices, it is black now, but it was once clear. And so what I'd like to do is I'd like to just probe inside of the candle to see what we might be able to see. So I'll just go down here. So you see the white smoke coming out. So this white smoke is the vapor of the wax. It is boiling off into a vapor. I'm going to put this a little further below. Now can you see it? Now can you see it? It is hard to believe that there's that much vapor being created by the candle. Now, to show you that is indeed this vapor that is lighting, I will attempt to light the vapor. And do you have a torch? There we go. Just getting a little bit of warmth here. Not quite happy with that yet. There we go. Can we have the lights down? This is the dancing candle flame. You see it dance? There we are. The wax is melted into a vapor. It evaporates, it goes through the tube to the top, exits in that beautiful shape, and that is what is burning in a candle. Oops. All right, thank you very much. Now, you don't need to be here at the Royal Institution in the theater to do this demo. Mike here will show us how we can do this at home.
Thank you, David. Thank you, Professor Ricketts. So exactly what Professor Ricketts has just shown you is that the vapor, indeed, is the part that actually holds the flame. So I have 2 candles here, and I'm going to try and reignite them in a fun way. For that, could I please get a volunteer? That hand went up first, so please come down. Thank you very much. Round of applause. And what is your name?
Sophie.
Sophie. Very nice to meet Sophie. Michael. Right, so Sophie, I'm going to demonstrate what I'm going to do. You can get the very nice candle, and I'm going to get this one. So what we're going to do is, we're going to take a splint here, and I'm going to light this. What we're going to use is what we've seen in that last demo. We're going to use the vapor from the candle to light it again. So what I'm going to do is this. I'm going to put the candle out, and then hopefully, very quickly, I can light it again. Did you see that? Shall I try again? Try this. Ooh. How do you feel about doing that? Yeah. Shall I get you a fresh one? Let's get you a nice fresh one here. Okay, so I will light this for you, and if you can hold it. Oh, the wicks are burning. There we go. That's the 3rd demonstration covered. We jumped a bit early there. Anyway, let's draw everyone's attention over here. And we can carry on. Right, Sophie, here we go. Here is your splint. I can do the snuffing out for you, and that way you can concentrate. So I'm going to take, if you just hold it a little bit higher than that to nearby, I'm going to hopefully put it out. Oh, sorry. This is the fun bit. There we go. Try a bit higher. Yep. Yeah! Round of applause. Thank you very much, Sophie. Now, that's beautiful and very impressive, and thank you to Sophie for showing us that. Now, we were experimenting, and what I'd like to show you is that sometimes you can actually make that vapor start and reignite from a higher point. And to do that, I've got a little bit of kit here. And hopefully, what I can do with this is create a much longer stream. Ooh, here we go. Try that again. If everyone could stop breathing, that would be perfect. Let's try one more time. Everyone breathe in. Hold your breath. Oh, I didn't mean it, really. There we go. Oh, I've got a snuffer.
Thank you very much, Mike. This is an original demonstration by Michael Faraday, and it is intended to be done at home with your parents. So there's one more demonstration I would like to do, and it's here. Mike, I may need your assistance if you can come join us. So I have a candle here, and I have a piece of wire mesh. And the wire mesh is of 2 different pieces, one on top and one on the bottom. Maybe you can show them with the camera. Can they see that there? See how there's a... Okay. So I'm going to attempt to split the candle flame in half. All right, can you just a little back? I have to still hopefully make it work. All right, so you'll notice firstly that as I move the candle closer, it doesn't penetrate the mesh. This is the principle upon which Sir Humphrey Davy's miner's lamp is made. The mesh cools off the flame so that it can't go through. But you may also notice that there's a little bit of that curious smoke above. So what I'm going to do is push this up, and then if you could back off until I get it lit. Okay. Go a little bit higher. Mike is right, there's quite the wind in this room. We had it there. Need this up a little more. It's there. Can we have the lights down? Can we have the lights down? Oh, I want to try it just one more time. Let's see if we can get it again. As Professor Faraday would say, a very pretty demonstration. And so, thank you very much. I'd like to talk next about the shape of the candle flame. And to do that, I have a toy from the Christmas market in Munich. So this is a series of small birds. One of them has flown off. I will just reattach it. See if I can get it attached. It may be too challenging for me eyesight. There we are. Okay. So inside of this is a candle. And I will heat the candle. Actually light it. There we go. You see it spin? I can do the camera on this one, I think. You can see it spinning. Little birds are flying around. So what's happening is the heat of the candle is rising. It's rising above, and it is spinning the little birds around. What happens in the candle flame is that the candle generates heat, which causes the air to rise above, and then the cooler, fresh air comes in from the side. And so the candle flame is shaped by that airflow from the side and up to the top. So my question now is, could we change the direction of a candle flame if we could change the direction of the air? And to help us answer that is Tom here.
So the professor has just described to us how the shape of the flame is influenced by the way the air is pulled in, and that, as the birds have shown, hot air rises. Here I have a cotton ball with some fuel soaked in it, so we have a lovely normal flame in more or less that pear shape that we expect. And to show that, as the professor has just described, it is the airflow that gives it this shape, I here have a extractor fan. It's going to control the flow. So I should be able to make this flame go on its side. And then for the audience over here, and possibly you. And if I'm lucky, sometimes this can be a bit difficult, I can hopefully make an upside down flame for you all.
So I next want to turn to how does the vapor come from the wick? How does the melted wax get to the wick? And I have here, I think I can do this with the demonstration camera. I have here a fresh candle. Now, this is just a piece of string. And so like wood or like paper, it's just going to burn if I touch it to the flame. So it starts to burn, but as it comes in closer, trying to find a good view for you, you can see it starts to melt the wax. And then that melted wax needs to find its way up the wick. And Tom is going to return with with a small demonstration to show us how that is done. Tom will return. While Tom is coming, you have no doubt seen this at your home. You may not have known it. If you have a sink or a basin with some water in the bottom and you lay a towel over it, you'll notice that the water crawls up the towel, well above the liquid in the basin. And this is called capillary attraction. And it comes when there's small holes between objects like fibers in a cloth or
Fuel through a salt.
holes in a pile of salt. And so Tom here is going to pour some liquid in. And then we can see that the salt does not light, but let us wait a few moments. And because of the capillary attraction, it is going up inside the little holes. And Tom, if you can do the demo camera, I will. You can see slowly how it is turning orange, orangish red. And let's just see, I'll give it a moment as it pulls up. And this is exactly what happens in the candle, is the small fibers of the wick pull the wax up as a liquid, and then the heat of the flame boils that liquid just like a kettle would into steam. Let's see now if it has come high enough to see if we could light it.
Break that off and poke it.
All right. And that is how the wax comes up the wick. You might say the wax is wicked up the wick. All right. Thank you very much, Tom. So we have shown you that it is the vapor of the wax that burns, that creates the flame. And in a true RI tradition, Dan is here to show us an amazing demonstration of just how beautiful that wax can burn.
So it's been suggested to us all that it's not the solid wax that burns, it's not the liquid wax that burns, but it is the vapor of the wax that burns. I have some solid wax in this test tube. You will note it is not currently on fire. I'm going to melt it with a blowtorch. It will become a liquid. It shouldn't be on fire. Let me melt it. As it becomes a liquid, it's not on fire. I'm going to get this liquid so hot, though, that it should be on fire, but because it's a liquid, it won't be. To turn it into a vapor, I'm going to dunk this very hot test tube into this ice water, breaking the glass, dunking the very, very hot wax into the liquid, boiling the water, sending the wax up into the air as a vapor, and it should be hot enough that it will spontaneously ignite. Let's see if it works.
So I think now we've convinced you how the candle burns. I now would like to turn to the question of how does it make light? And so we used this tube before to probe into the candle to see the wax. And now I'm going to, instead of going all the way down to get to the base of the flame where it's boiling that wax, I'm going to go a bit higher. And let us see. Can you do the demo camera for me, Mike? Can some of you see some black smoke coming out? So I'm just going to put this over to see if I can capture some. It's hard to see. Oh, you can see it. Oh, there you go. So this black smoke is unburnt carbon. The candle is vaporizing the wax. Some of the carbon in the candle wax is burning, but not all of it. And so it is not the reaction of burning that creates the light, but rather it is the heat of those carbon particles. Incandescence. We are going to heat up the carbon particles so that they will glow because of their temperature, not because there's a chemical reaction. And so I have a flame here that has very little yellow in it. And if you could turn down the lights, and it'll just be a very small, but reddish there. You see that? You see? There we go. I'll move a little bit to see. Can you see that? You see that yellowish? That is just me heating the carbon particles so they're hot enough to glow. I think we've got that. Excellent. Thank you, Mike. Mm-hmm. So we did not understand this until Professor Planck put forward his theory of black body radiation. And simply put, if we have a body and we heat it up, it starts to emit light. You may have gone to charcoal that perhaps did not seem lit, but you put your hand next to it and you could feel the warmth. It starts in the infrared where we can feel it as heat, and as it becomes hotter and hotter, it moves slowly into the visible range, into the reds and the oranges, into the yellow, and eventually what we would perceive as bright white. And in fact, that is why the sun is the color it is because of the extremely high temperature that it burns at. And Mike here is going to show us a couple demonstrations about black body radiation and how things can emit light. Thank you, Mike.
Thank you. So what we're looking at here is putting the ideas, not only from this lecture from Michael Faraday, from Professor Ricketts, but also Max Planck, into action. I've got a piece of very thin wire. It's in a specific shape, but hopefully that will become apparent in a minute. What I'm going to do is send a massive amount of energy, a massive amount of electricity through it. As I start, the amount of electricity will be low, and so you won't see anything. But it is actually warming up. I can feel a certain amount of heat. So going back to what Professor Ricketts was saying, when there's very low energy, there might be heat, there might be some light, but it's infrared. Now, if I am to turn this up a bit higher and add more energy, it becomes hotter. And what we should find is that if we bring the lights down a tiny bit, thank you, Josh, is that we might see this start to glow. Now, from the middle of the audience, and maybe for part of you over there, you might see that it does read out RI. But just to prove that it is very, very hot, I can take a candle, hold it to it, and there we go. A very, very overextensive candle, but showing you that this is indeed very hot, and the hotter it gets, the more heat and light it is giving out. Over to you, Jason.
Thank you, Mike. So as Professor Ricketts and my esteemed colleagues have talked about, light sometimes cannot always be visible, but it is giving off a lot of heat. Now what I have here is a very special blowtorch, and I'm going to turn it on. And there is a very, very small flame. I don't know if some of you might be able to see a very small blue flame there. And I'm going to use this very small blue flame to light this piece of chalk. So can we get the lights down a little bit, Josh? Thank you. So hopefully the audience in the front should be able to see the chalk is glowing bright yellow to white. And that is because the heat from the torch is heating up the chalk, and that is what glows. I'm going to move this over here.
Okay.
Oh. So you can see I'm heating it up with the blowtorch, and you can see the chalk is getting very, very bright white to even yellow. And once again for this side. Now, funny story about this. This is where the term limelight comes from, because we are heating the chalk with a very, very hot ignition source, and the chalk is actually what gives the light and the ignition to give that limelight. Thank you very much.
Now, if you had any trouble seeing either of the previous demonstrations about particles getting hot and showing and glowing bright, this next demonstration should hopefully rectify any of that. And here to join us is Jin and Millie.
So, what Millie has in her funnel and all over my clothes is corn flour. And as we established earlier, the color of the flame comes from the incandescence of the carbon in it. Now, what Professor Ricketts did isn't up to our RI standards. It's kind of bad, it was kind of small. So we're going to give you something bigger. So this incandescence is true not just for the carbon that comes from a flame, but from carbon from other sources, including the carbon that we find in our food. There we go, really. Classic demo. Thank you very much.
I would just like to remind Jin that this lecture is about a candle. So being small is no deficiency. So what does it mean to burn? That is our next question. I think we take it for granted that burning happens in everyday life, but is burning something special, or is it something that happens all the time? Burning is simply a chemical reaction. We take two pieces, we bring them together, and in doing that, they release energy. These are called exothermic reactions. And we see commonly wood or charcoal and oxygen to burn to do a flame, but we can see burning in many other forms with many other chemicals. And so, Isla here is going to show us some very interesting chemical reactions that are exothermic, or in our context, perhaps burn. Isla?
Thank you, David. All right, thank you. So we've been talking a lot about burning and combustion. We've seen lots of fire. But I'd like to ask you, what do you think? What's the most flammable thing that you can think of? Can I have some answers from the audience? Can anyone give me, like, the most flammable thing you know? Yeah. Fire? Fire? Yeah, fire is pretty, it's in the name, isn't it? That was a silly question from me. But someone said brandy, I like that. I like where we were thinking a bit Christmassy. Yes, in the white t-shirt. Petrol, I love that answer, because that's exactly the one that I had in mind. I know there are lots of different answers, and there are lots of things that are flammable, but petrol is the one that I also had in mind. I thought, what can we get that's going to make a huge flame? So I do have here a bowl of, oh no, I won't do that. That's not a good idea. There is fire everywhere, like you said. Fire is flammable. I'm just going to pop the petrol there, and I want to show you just how flammable petrol can be. Obviously, I'm sure you're used to the idea of petrol. I'm just going to put some gloves on so I can stay nice and safe. Oh, these gloves are a little bit funny, but that's all right. And I'm going to take a little bit of cotton wool. There we go. I'm going to dip it in the petrol for like half a second, like that. So there's only a tiny bit of petrol on there. And then I'm going to use one of these flames to burn the petrol-y cotton. So you can see it burns this beautiful yellow flame, and it's flammable. It's flammable. But I thought, you know what, we need to go a little bit bigger. We need to go better than that. And here at the RI, of course, lots of things have happened in our 225-year history. And one of the things that has happened is the discovery or the isolation of different chemical elements. And the most reactive of those that I know, that I could get my hands on, was sodium. Who's ever seen sodium explode before? Yeah, quite a few of you. Yeah, it's a pretty explosive reaction, right? So I thought, why not combine sodium and petrol? Yeah, what could go wrong, right? But just in case it does, Dan's going to bring some safety equipment. So we will combine the two of my favourite things, and we will see what happens. So in my test tube, I have a tiny little bit of sodium. It's a little bit hard to see because there's a tiny, tiny bit. But trust me, it is in there. Can some of you see that? Maybe in the front row, you might be able to see, yeah, it's just like, it's this beautiful kind of silvery material, and you just might have to take my word for it that there is a little bit of sodium in there. But that's all right. We will hopefully see it explode or catch fire in our petrol. So I'm going to pop that there, and I'm going to tip the sodium into this highly flammable petrol in 3, 2, 1. So that was pretty disappointing, right? And it is exactly like Professor Ricketts said earlier. Burning or combustion is a chemical reaction, and it doesn't always kind of happen in the way that we think. Sodium is a metal that reacts not with petrol, but with water, and that is the reaction that many of you probably have seen. So let's try it out. I'll pop this to the side. Maybe I can ask Dan again to take that away. And I will replace this with some water. And in here, I have a bigger chunk of sodium. So now, yeah, ooh, that's right. So you can actually see that. Some of you might be able to. So it's a little chunk there. It's about a centimetre, little nugget in there. But I promise you, you will be able to see this once it hits the water. Well, I hope you will anyway. And if you can't see it, hopefully we can hear it. All right, here we go. 3, 2, 1. There it goes. You can hear that fizzing. Now, sodium's usually stored in some mineral oil because it reacts so violently with water. So it might be a little bit of that mineral oil that's kind of seeping out. Oh, there it goes. And we have that burning reaction. Oh! There we go. Thank you very much.
Rather big explosion there. So I want to next turn to the question of, do you notice anything funny? I have almost a brand new candle, and I have a candle that's been used quite a bit. So the question I have for you now is, where did the candle go? Right? It's not inside the little glass. It's not on my hands. It's not on the table. We are now going to turn ourselves to where does the candle go? And you know it burns, but the question is, what does it turn into? Where does it go? What does it become? And to answer that question, Tom has built a lovely little apparatus here for us to investigate this. Tom, would you explain what you have set up here?
So the professor has asked me to put something together to show what comes out of the candle. So obviously here we have some candles. The funnel will capture what is released from them. It comes through the tube. The first thing it hits is this ice bath to cool down everything, because obviously, as we've learned so far, the candle's very hot. And then this final flask is full of lime water, which we use to identify one of the things. I won't spoil it, it's coming later. Just to speed this along a little bit, I've got a pump that'll increase what's being drawn through. Some of it will be getting out here. So, again, not to spoil the next step. Any of you can turn the suction on. Come on.
So Tom, this is now pulling the output of the candle through the tube.
Yes.
And out.
Yes, much more directly than before. And if I lift this up now, we should probably have enough for this part. So whatever gases were in here have condensed into something. I'll give that to you, Professor.
Thank you. So we have a clear liquid in here that we used the ice there to condense so that we could have it in its liquid form. And for all of you that may watch this in a repeat, I just want to let you know we ran this for a long time before you came here so that we could get enough water to do this. And I maybe have spoiled it there. I think it is water. It looks like water. But to show it's water, I think what we should do is test it with a bit of sodium from Isla.
It's the only way to test if it's water, obviously.
There's probably a safer way, but that wouldn't be nearly as much fun.
All right, maybe I'll just grab the shield just in case.
saw what happened last time.
Thank you. So we think we have water in the white container, don't we, David?
It certainly looks like water.
Well, there's absolutely only one way to find out. So here we go. Oh, come on. Oh. I think it's water.
I do think it's
Yeah.
water. So we've shown that one of the products of the candle burning is water. And you may know that water is composed of hydrogen and oxygen. The oxygen we get from the air, where do we get the hydrogen from? From inside the candle. That is one of the products that burns. And what I'd like to do is, now that we've seen that water is one of the products, is I'd like us to learn a little bit about the physical properties of water, because it is used so much in our daily lives. And to show us some very interesting properties and demonstrations are Tom and Jason.
As we've just described, water, brilliant compound. We use it for a lot of things. One interesting property that you might know about, you certainly know about, but you might not be fully aware of, is that when it's frozen, its solid form, it actually expands. It's bigger than in a liquid. It's less dense. That's why your ice cubes float. So what I've got here is some dry ice, which is around -70, I'm rounding a little bit, in an alcohol solution. So it's much colder than the freezing temperature of water. And in here, these metal balls are filled with water. That's why they're in the water. I filled them underwater to make sure there's no air. I'm going to drop these in, we're going to let them freeze, and we'll see what happens, and we'll let Jason's run. Be aware, you might hear it happen. We're going to come back to it at the end of Jason's.
Ooh, that sounds very interesting down there.
Oh.
As some of you may already noticed, I have been boiling this can, and you might be able to see some white smoke coming out of it. That white smoke is steam. It is not smoke, and that is because I've got a little bit of water down the bottom, and it is being boiled. Now, I'm going to put some safety gear on. Now, it's being boiled so much that, there you go, you can see the steam coming out. Now, what I'm going to do is I'm going to show you the difference between water vapor, steam, and what happens to the vapor when it's quickly dunked into ice-cold water. So now it's been steaming. Whoa! Hello!
Did you notice it?
Did something happen? Whew. That was magnificent. Nice one. Well, this is going to look really small now. I'm going to try it anyway. So I'm going to dunk it upside down in cold water, and instantaneously the can implodes. Very, very different to what happened just there. Tom's one absolutely exploded and went everywhere, whereas this one imploded, and that is because of that water, the steam that was inside. Once it was dunked into the cold water, it wanted to turn straight from steam back into a solid, so it wanted to turn back into water. And the pressure from all around us in the environment that we have crushed it, and now we have a can that is full of water, but also because of the pressure differential from the outside, has absolutely crushed that can. Oh, thanks so much.
So obviously you noticed something there, but just to get it out, what you'll be able to see. So here, I'll show one, and there's a few in there, so might be able to see a different thing. The ice it's frozen, it's expanded.
That's not going to explode, is it?
This one won't explode, no. All the energy went already. So don't touch this, it's very cold, but you can see there's a crack there where the ice is coming out.
Tom, maybe we can do a camera
Can we do a
shot?
camera, of course. So these were sealed. I'm trying to get the angle here. There's a little crack here. There'll be a better one in here. Let me pull it out.
Did they all three blow up?
Felt like it.
Yeah, felt like it. I'll get that, don't you worry. Here's the best example. So it has literally blown the entire thing apart. It looked a little bit like that one, although this has cracked. That is the power and the need of expansion that ice will have going from liquid to a solid. Thank you.
Now, I think you know the answer, but as philosophers, we should ask, is water an element or a molecule? And what we're going to do here is see if we can't separate water into its multiple parts and see what we can learn from them.
I'm gonna get my goggles, sorry.
And Michael is going to go be safe. Not that there'll be more explosions, but there will be. Just turn this up a bit.
So, what we have before us is a setup which is quite similar to something that a very important person to the Royal Institution would have used many, many years ago. As Isla has mentioned, several different elements were isolated or discovered here. And one of the main methods that were used to do that was electrolysis. And we have a very simple electrolysis setup here that could have been used if Humphrey Davy was alive today. So what we have is seen some of the properties of water, and now we're going to use electricity to break it apart and look at some of the properties of the gases that come from them.
Okay.
And to do that, we need
We're
lots of
putting these on.
protection. So when we do this, we would appreciate it if you could cover with flat hands your ears, because there might be quite a sharp sound. Are you ready?
No.
Oh, ready? No. Good. Goggles? Oh, just in case.
Thank you.
So first thing I'm going to do is make Professor Ricketts the bomb sight. So if I could just have your flat hand here, I'm going to put some bubbles in here, make it nice and wet so we don't actually set light to you. And then a bit more. Is that enough? Nod when there's enough. And we're going to look at the liquid coming out of here. So what you might be able to see is quite a lot of bubbles forming here. And on 3, 2, 1, I'm going to detonate them. So if you can cover your ears now on 3, 2, 1.
So Mike has just shown us that we can, with electricity, take water apart, and then when we put it back together, energy and heat comes out. And in fact, this is an idea for a new renewable energy car, where we would take the products of water with us, we would recombine them, extract the energy to drive the car, and the output would simply be water. I'd like to, however, look a little bit more closely at what are those elements of water, and Isla will return with us to show us those.
Thank you, David. All right, so here I have a contraption that's going to help us see that water is made of different atoms and different elements. So what's the kind of scientific way of saying water? H2O, there we go. And that is 2 hydrogen atoms to 1 oxygen atom, making up H2O. So what I have here in my container, thank you, Millie, is some H2O with a little bit of electrolyte in through the middle there. And we're hooking it up to a benchtop power supply. Similar to what my colleagues just did earlier, we made some hydrogen and oxygen together. This contraption, hopefully, will separate out the hydrogen and the oxygen. So once that starts up, hopefully we should be able to see that there is a little bit of bubbling that should happen. Might need to give it a little moment. Bump that up. Yeah.
To 30.
To 30, he says. All right. We're at 1, by the way. So bump it up a little bit more. Whoa. Yeah, great, great. But what we should see is that because we're passing electricity through that water, we should have oxygen collected at one electrode and hydrogen collected at the other one. Right, still bumping up. Oh. How's that? Oh, there we go. You see that bubbling? Might need to grab this. So those of you at the front might be able to see, but also you can see that bubbling, right? And there it goes. And if we give it just a few more seconds, hopefully we can see that there is more gas being produced at one electrode than the other. Although that doesn't seem to be happening, and I'm not sure why. The ghost of Michael Faraday might not be with us tonight. But in theory, we might also have a leakage. That's probably the more likely reason this isn't working. But we should have some hydrogen being produced at this electrode here. And actually, you might be able to see, again, this one's clouded over a little bit, so it's a bit harder to see. But the one on the right-hand side, the clear one, you can see that the balloon has kind of inflated a little bit more so than this one. And there's much more vigorous bubbling happening over at this electrode, which shows us that there is twice as much hydrogen being produced compared to the oxygen, because water is, of course, H2O. And I'll hand back over to David, who can tell us more about it.
So I want to talk a little bit more about hydrogen and about oxygen. And specifically, we're going to examine it in two demonstrations that are coming up. Dan is a little peckish, and he asked if he could have a snack in the middle of the lecture. And I said, only if you could turn it into a demonstration. So Dan, can you teach us a little bit about oxygen?
Absolutely. So I have here my snack. I have a muffin. Lots of energy in that muffin. So if there's lots of energy in there, we might be able to think of it as a fuel. So I'm going to try and set it on fire. There we go. And you will observe that the muffin does not burn very easily. It's quite moist and lovely, and but all that moisture is making it very difficult to burn. But perhaps if I give it an abundance of oxygen, lots and lots of oxygen, that will help it burn. And back here I have some liquid oxygen, which I will liberally splash over the muffin. Oh, there goes the... That's back on. Well, good, I needed that anyway. So now let's see if the muffin will burn with all that oxygen. More oxygen? More oxygen. We need more for later, so I will leave the rest there for later on. But with lots of oxygen, it's really easy to burn things. There's that reaction happening. The carbon in our food burning with the oxygen that we supplied it. It burns so hot, it appears to have cracked my bowl. Really quite nicely as well. Look at that. Clever. Now, for something else that burns really well, another really good fuel, I believe Millie has a hydrogen balloon for you.
Whoa.
Sorry, I realised that was going to be a problem. Oh.
Right, I'm going to get all the necessary PPE on. But this is a pure hydrogen balloon. And you might know already that hydrogen is very flammable. So especially in, well, solely in oxygen. So if I light the splint and then break the balloon with the splint, that should mean that the hydrogen can leave the balloon and react with the oxygen in the air, which will cause a big explosion. So put your hands over your ears and ready. 3, 2, 1. Yeah. And now we're going to show you some other things with hydrogen.
So we've just seen that both hydrogen and oxygen can be vigorously involved in burning. If you notice, the hydrogen balloon was floating upwards. It's because hydrogen is lighter than air. Oxygen is more the density of air, but that hydrogen flows upward. And I saw the oxygen helping the muffin burn, and I saw the hydrogen, when it was burst, mixing with the air to burn with the oxygen. And I thought to myself, if hydrogen is so explosive, so easy to burn, could we put a fire in a pure hydrogen balloon? Would a fire burn in pure hydrogen? To answer this question, it's Dan playing back with some more balloons and fun.
So here's another balloon of pure hydrogen. Inside of it, though, is something some of you might be able to see. It looks like this. I want to show you what this does, first of all. Here I have a piece of nichrome wire, the stuff that Michael used earlier to make that glowing RI, and it is wrapped around a little piece of flash cotton. This is the thing magicians use, and they use it to make a puff of flame to distract you while they're doing something over here. They go, and then they swap a card or something. It is a nitrated cotton. What that means in very simple terms is it has a fuel, and it also, in its molecule, has oxygen ready to bond with that fuel and burn, but it's kept apart by something like a nitrogen. And with a little kick, say from a hot wire, it can very quickly burn completely. So if I hold this up, I'm going to ask Millie to send a current through in 3, 2, 1. And there was. There we go. So we had a bit of fire there. Yeah, thank you. Why not? Thank you very much. So that is what I have inside this pure hydrogen environment, inside the balloon. So I'm going to attach this to the circuit so that Millie can send electricity through, maybe away from those candles there. So again, pure hydrogen environment. Our flame is inside. I'm going to cover my ears. I think you might want to as well. Let's give Millie a countdown. 3, 2, 1. Okay. Maybe you don't think it's really hydrogen in there. Millie, could you prove to everyone it's hydrogen? Please cover your ears. Oh.
3, 2, 1. Oh, there we go.
Hey. So the flash cotton had the perfect amount of fuel, the perfect amount of oxygen. There was no extra oxygen for the hydrogen to burn with, so the hydrogen didn't take part in that chemical reaction. However, here I have the same setup, but this time I've put some hydrogen in the balloon. Some oxygen in the balloon. So there's our little e-match, or our little bit of flash cotton with the nichrome wire. There is some hydrogen in there, but now there is some oxygen in there for the hydrogen as well. I suspect that this is going to be very, very loud. You definitely need to cover your ears. Give us a countdown. 3, 2, 1. Whoa, very good. Professor Ricketts.
Well, I think we now understand that indeed you can't burn in pure hydrogen. We do need oxygen. And we've learned with the muffin, by the way, no, I don't think it's edible now. It's going to offer it up. So we know in the air we have oxygen. We've shown that burning with the candles that we have right here in front of us. The next question I have for you is there anything else in air other than oxygen? And if so, what is it? And to explain this to us is Jin.
So when Faraday originally did these lectures, he was removing oxygen from his air using what he called a reddening gas. And what he found was that what remained was inert. It didn't react with anything. Now, what he was using to remove that oxygen was nitrous oxide, which we couldn't get past health and safety or our legal team. So I opted for something different. In these bottles is a solution of methylene blue. Now, if this extra gas in the air doesn't react, this should not react either. So let me just show you how it works first. So in here is just normal atmospheric gas. If I give it a shake, it should turn blue. So it reacts with the oxygen in the air and it turns blue. Let's see if this is the case for this bottle, which I filled with that mystery extra gas. So let's give it a good shake. And indeed, it remains colorless. Now, just to show you that it's not reacting, hello, Thomas. I am going to try and light a flame inside. Now, as we established earlier, a flame is simply a chemical reaction. And if this does not react, we should see that the flame does indeed go out. So let's put that in. And indeed, it does. And just to show you that this isn't just water in here, it isn't just something random, I'm going to reintroduce the atmosphere. Very scientific. I'm going to seal that back up, give it a good shake. And you should see that it goes blue once more. Now, turns out that extra gas that Faraday found was nitrogen. It makes about 70% of our atmosphere, but we still have some other gases left that we need to talk about. Thank you very much.
So I think we need to finish answering the question of where does our candle go. Very interesting that the small one survives. Maybe the explosions were too big for the tall one there. So we're going to return to Tom's apparatus and look at the flask at the very end. And tell us a little bit about what you're doing there.
So, as I said, I'll just lower this down because the candles are burnt down a little bit. So as before, it's running through. It's going to go into the ice bath, and now we're going to have our second liquid. This is lime water, which the professor is going to tell you a little bit about to help explain what's going to be happening here. There you go.
So this is just a small bottle of lime water, and lime water, one of the things it does is this is just dry ice, which is frozen carbon dioxide, and we can test for carbon dioxide simply by putting it in lime water. And it's a little hard to see initially. I'm going to put the cap on just gently, and I'm going to move it back and forth. Can you see it's turned milky white? Yes? So this is our test for carbon dioxide, is we put carbon dioxide into lime water, and we see does it turn milky or not. And so that's what we have here in this flask at the end. And so now what we'll see is, can we detect carbon dioxide?
Will the camera reach here? Not really.
There we go.
And you can see it's starting to go a bit cloudier. It's certainly not the colour of normal water now. Can I have that beaker to show it's similar?
Ah. And there we found that the final product of the output of the candle is carbon dioxide, the oxygen from the air around us, and the carbon from inside of the candle. Thank you, Tom.
Thank you.
Now, we learned a little bit about oxygen and hydrogen. We noticed that, for instance, hydrogen was much lighter than air, and so it floated. To share with us some interesting facts about carbon dioxide, Judith and Jason will join us to talk about those properties.
Thank you, David.
Hello again. So Jason's bringing over a bucket with dry ice, which is very, very cold carbon dioxide. What's happened here is that the carbon dioxide, which is very dense, has pushed out all the air and the oxygen, and it means that there's only carbon dioxide in this bucket right now. And to prove that to you, I'm going to blow some bubbles. So if we blow some bubbles, they usually kind of just fall down and drop. But if we blow the bubbles into the bucket, don't know if you can see that, they will actually float because they're made out of air And the carbon dioxide is pushing them up all the way. Ooh. All the way back up. Now let's have a look at what happens. Oh, maybe you can see that with the camera a little bit better.
One just popped.
And the last one is just about to pop.
We might be for a while.
I think it's going to stay there. Let's have a look at what happens if we burn something in there.
Yeah, so like Professor Ricketts and Judith just said, this is a box of carbon dioxide. It's an invisible gas. And you can see that a bubble is hovering on it, kind of like magic. So what happens if we take something very, very flammable, safety first. If we take something just like a bit of cotton wool, put in some petrol, why not? And we set it on fire. So you can see that that is burning very, very bright, and you can see that it is definitely on fire. What happens if I put it into the carbon dioxide, though? What do you think will happen? So, an explosion. Ooh, oof. So I'm going to put it all the way into the bucket, and it extinguishes. Now, that's a really interesting thing there. So I'm going to relight it and do it again. It's because carbon dioxide is denser than air, so it sinks down to the bottom. And without oxygen, things just cannot burn. So if I do this really, really closely and slowly, you might be able to see the bottom of the cotton bud slowly start to extinguish, but the top is still going to be lit up. So let's give it a go. Oh, thank you, Mike. So it's completely lit. And that is, you can see that I'm just hitting that layer of carbon dioxide now, and the bottom of it is starting to extinguish, but the top is still lit. If you get any closer, that camera is going to catch on fire. And then once again, if I completely dunk it, it goes out. Thank you. Now I hear some of you saying, what if we get something that doesn't need oxygen to burn? Will it still burn in the carbon dioxide? Well, I have a strip of magnesium here. That's right. Now, there is a bit of a warning. Do not stare at the bright light. It will hurt your eyes. So try not to look at it. I know it's going to be very, very... you're going to want to stare at it, but don't. Just try not to, all right? So I am going to light it up with this blowtorch, and I'm going to drop it into the... Oh, yes, that's probably a really good idea. Thank you, Dan. I'm going to light this magnesium, and I'm going to drop it into the carbon dioxide. So I'm going to let it go. So it's very bright. It's very much burning. But what happens if I drop it in? So it looks like it's actually burning a lot brighter. And that's a really interesting thing that's happening here. So the magnesium it actually strips the oxygen from the carbon dioxide within the cube. So it's actually taking out those oxygen atoms, and it's actually creating something, now that it's finished burning. You might be able to see this white thing. This is actually magnesium oxide. So it's taken all of that oxygen to create that really bright burn that you saw before. And then what's left is actually the magnesium and the carbon, which is magnesium oxide. So all of this stuff is just magnesium oxide. Thank you very much. Oh.
So we come to our final act this evening. I said that we would learn not only about physical phenomena, but also about ourselves. And so for this next demonstration, Michael, if you could help me find a volunteer.
Yes, we choose a volunteer. I'll have to go this side. Yes, maybe with a star at the front. Is that a star? Maybe not a star. Round of applause, please. Let's come down. We're going to come over here.
All right, and what is your name?
B.
Hey, say again?
B.
B, okay. B, may I touch your forehead?
I don't mind.
She's quite warm. How is it you're warm?
I don't know.
She's not unlike a candle, is she? But she doesn't seem to give off any light, but we'll maybe look at that shortly. All right, Bea, I have here a flask of lime water, and we've sanitized both of these ends. What I would like you to do is I'd like you to inhale through this one, just, and if you need to take a breath, take it out, inhale again, and I want to see if we see any carbon dioxide coming in from the room into this lime water. Can you hold it? There you go. And inhale. Nope, try again. Okay. There's nothing, no carbon dioxide in the room. Now I would like you to exhale. Again. Again. One more time, because it's fun. Do we see that the water has become milky white? There must be carbon inside of you. Do you eat carbon? You don't nibble on a bit of charcoal? Well, clearly we have carbon dioxide, and we know it's not coming from the air, so it must be coming from you. Do you eat sweets? Yes. Treats, like delicious treats and sugar? Well, before we go and explore that maybe sugar is where this carbon is coming from, I just want to make sure that you don't have a candle in you. Could we turn down the lights? Could you just open your mouth and say, ah? Yep, there's no candle in there. So I'm thinking it might be the sugar. And to explain how carbon is in the foods we eat and in sugar is gin. Thank you very much, Bea.
I want to preface this by saying this is Professor Ricketts' wife's favorite demo at our demo day back in June. It is the most exciting demo of this show. It's very explosive. It works very quickly, so it needs just as good of a countdown. So can everyone give me a 3, 2, 1? Wow, amazing. No, I'm kidding. It does take a little bit of time. In the meantime, Isla is going to show you something really, really cool.
Isla's going to come on. Come on, Isla. Come on.
Okay.
And so Jin will come back and talk to us about carbon. But one of the things we take for granted is that carbon turns into carbon dioxide, turns into a vapor. Not everything that burns turns into a gas. Some things remain a solid and even become heavier. And Isla will show us that with her demonstration here.
That's right. So what I have here is some wire wool or steel wool, and it's made of lots of different metals, but it's mainly made of iron. And iron has a really interesting property. When it burns, like Professor Ricketts said, when things burn, we often think of things just kind of disappearing or becoming a gas and going somewhere. But iron burns in a really interesting way, and it actually gains things from the environment. So I'm just going to pop this on here. Hopefully you'll be able to, we'll just tear it a bit. And I want to show to you, I want to prove to you that iron indeed gains things from the environment. So once I pop this little bit of iron on, sorry, it's a little bit dark, isn't it? Can we see that all right? All right. Oh. So we're tearing it. It's about 0. And I'm going to, well, what I'm just doing here is trying to separate out the iron, the bits of iron, so we can have as much oxygen surrounding that iron as possible. Oh, yep. No, it's the same size. Yeah. Oh, maybe this tile, yep. All right. Well, lucky there's so much stuff out here that we can, between us, there's something that will fit the bill. All right, here we go. Here we go. So it's 0 now. I'm going to pop it's about 20.2 grams, 20.20 grams of wire wool, and I'm going to set it alight using a 9-volt battery. Pop a bit there. Ooh, there we go. And I'll start it off there as well. It's very warm, and it's very pretty, but what I'd like you to see is that the numbers are going down initially a little bit, but hopefully we'll be able to see the numbers go up again. So remember we started at 20.20 grams, and now we've gained about 0.2 grams, 0.3, 0.4 grams of oxygen. So what we're creating here is iron oxide, which is rust. Now, what we're doing is taking that oxygen from the atmosphere and it's combining with the iron from our steel wool to actually create that rust. And the reason we can set it alight using just a 9-volt battery is that the wire is so fine that it just kind of short circuits and creates this beautiful effect. So it's going to go up, and like Jin's experiment here, it might take a little while, but we can still see that the numbers are rising. We're at 21.9, almost 22 grams. So we've almost gained 2 whole grams of oxygen from the air around us to create iron oxide. All right, thank you, Michael. I think it'll be all right.
So I think Isla has shown us that if we used iron to fuel our bodies, this may be a problem. And so we see here the sugar has created a snake of carbon. And Jason is coming back here to show us why carbon is such a beautiful fuel for our bodies.
Thank you, Professor Ricketts. So I have here a very big flask. And do you know what comes with a very big flask? Hopefully a very big explosion. So I'm going to get this potentially dangerous thing out of the way. I am actually going to take the pure carbon that Jin created from the carbon snake and I'm going to add it to this flask and we're going to see what happens to it. So I'm going to take some of that liquid oxygen that we used earlier, I'm going to pour it into the flask. Yeah. Why not? And then, wow, that's still going. That's crazy. I'm going to break a little bit off. Ooh. Now, this isn't going to react just with the liquid oxygen. It's going to need a little bit of a heat source. That's why I've got a blowtorch. So I'm just going to heat it up. Ooh, maybe not that much. I'm going to heat it up with my blowtorch, and you can see that it's glowing a little bit red as much as I heat it, and you can see that it's glowing bright red. So if I drop this in, we should see a reaction. Ooh. And what you're seeing there is the carbon reacting with the liquid oxygen because it's a really powerful oxidizer. I'm going to try it again with this one. And once again, once it touches that liquid oxygen, it pretty much disappears. Now, you might not be able to see very much in there at the moment, but the really cool thing about this, and Professor Ricketts alluded to it before, is once carbon, where does it go? And this is the beauty about carbon in our food. It actually disappears and turns back into carbon dioxide. So all of this gas that is coming out is actually carbon dioxide. Do you want to see it again with more carbon snake?
Yeah. You have a piece right there.
Oh, I do. I have a massive. Thank you. Ooh, see if I can get it in. Hey. So it's very beautiful. You might actually be able to see it with the lights down. The carbon actually disappearing in the liquid oxygen. So that is the beauty about carbon. And I'll pass back to Professor Ricketts.
Before we finish our lecture, I think it's only appropriate that we bring out the true hero of the story. Charlotte, can you bring on Faraday's candle? If you want to walk and show us that. Complete with the wax. She won't let us use it in the demo, I don't know why. Don't touch. Thank you very much, Charlotte. Let's give her a round of applause. I can say to you at the end of this lecture, for we have to come to an end at one time or another, is to express my wish that you may, in your generation, be fit to compare to a candle. That you may, like it, shine as lights to those around you. that in all of your actions you may justify the beauty of the taper by making your deeds honorable and effectual in the discharge of your duty to your fellow man. I think it only fitting that we end this lecture by making a candle, a very large candle. So what we have here is a tube all through the audience, and Dan is going to be filling it with
Very explosive gas.
a very explosive gas. So the audience will start to blow up over here and slowly move over. So Dan will fill this tube with gas, it will ignite, and we will see a flame travel through all of you in the audience, down onto the floor here, where we will light our candle. Dan, I give it to you when you're ready.
You guys ready? Yeah? Audience ready?
You ready?
Hold the tube up in the air. All right, here we go. Wish me luck. Oh, did it not make it? Shall I try again? Here we go. What? No! Yay!
Who wants a bigger flame? Yes. No, some glasses. We may do it. We may do it a second time, so save some. All right. May I have the lights down? And can I get a 3, 2, 1?